normally. But yeah, before we get started, I will just quickly tell you where we met. We met at the Hannover Fair at the shared booth of Schleswig-Holstein, which is organized by the HY.SH every year. And for us, it was really interesting to hear that Fraunhofer ISIT is also working a lot with hydrogen, because we thought, okay, Fraunhofer ISIT, they do batteries. That's great. Of course, you can also connect batteries in a really efficient way with electrolyzers to optimize the running hours of the electrolyzer. But in this case, we talk about the storages. So for us, it was really interesting to hear that the connection within an intelligent grid at the Fraunhofer ISIT and the role of hydrogen is also a part of your research. And that's where I would like to give the word to our today's guest, Dr. Qian Xun. And we are really pleased to have you here. And I hope it's also a quite interesting opportunity for you to present your current research. Feel free to unmute and start with your presentation.
Hello everyone. Very welcome to my presentation. My name is Qian Xun, and I'm from Fraunhofer ISIT. I'm mainly working at the Center of Electronic Energy System at Fraunhofer ISIT. So, firstly, I would like to briefly introduce myself and also my group. So I received my PhD degree from Chalmers University of Technology last year. So I also joined the Fraunhofer ISIT last year. The Fraunhofer ISIT is part of the extended research community in northern Germany with 2 locations. Its headquarters with 2 clean room facilities in Itzehoe under the direction of Professor Kappels, and the newly founded office in Kiel with 2 laboratories in low and medium voltage, headed by Professor Michael Lizery. So Professor Michael Lizery is also the head of the chair of polytronics at Kiel University. Our group is mainly focused on hybrid grid, active reliability, and battery integration. So here comes today's agenda of my presentation. Firstly, I will give a brief introduction and motivation of my presentation. In the second part, I will introduce the system architectures in applications of data center and residential communities. In the third part, I will show how the framework of the optimal size and energy management. In the fourth part, I will show some results for the case studies. Finally, I will conclude my presentation. Let's start with the introduction part. This figure shows the CO2 emissions by different sectors from 1990 until 2018. So as we can see here, the world CO2 emissions increase significantly every year, especially the electricity and heat as a major contribution. Apart from this, the transport, manufacturing, construction, and buildings also contribute a lot to total CO2 emissions. One way to reduce CO2 emissions is to increase the capacity of renewable energies. This figure shows the estimated capacity of renewable energies in Germany until 2045. So there would be a huge number of PV and wind turbine installations in the following decades. It shows that around 17 gigawatt increase every year. So until 2045, it would be around 700 gigawatt renewable energies. So with the increase in renewable energies, there are also some challenges. Due to the inherent nature, the renewable energies show intermittent uncertainty and distributed generation. So the generations of PV and wind turbine are highly dependent on solar irradiance and wind speed. As we can see, these two figures, they show how the PV generation and the wind turbine generation change according to the different times in different days. So in traditional microgrid, it is designed to be the centralized and one-way power flows. In this scenario, it is hard to forecast and balance the supply and demand. So then the major challenge is to balance to achieve the balance between the supply and demand. Energy storage with various types of skills with could meet challenges of high volume PV and wind turbines. So at the greatest scale, we can use energy storage, for example, battery to charge at the low prices and make good use of midday exercise supply of PV, for example. And also with the energy storage, we can also collocate with utility scale PV and wind to smooth output of the grid. And discharge to mitigate steep ramp and late afternoon peak. With the rooftop PV, we can also use the energy storage to minimize backflow on distribution to increase the circuit hosting capacity. On the other hand, we can also use energy storage to manage local variability and also flatten load profiles. So how to select the types of different energy storage device? As we can see here, this is a Ragani plot of different energy storage devices. The x-axis is the power density, while the y-axis is energy density. So for the fuel cell, it is an energy conversion device. So the energy is stored in hydrogen. For the fuel cell, it has high energy density due to the hydrogen, and also, but it shows low power density. For the supercapacitor, it has high power density and low energy density. So for the supercapacitor, it is more suitable to deal with the high dynamics. For the battery, it shows moderate power density and energy density. So how to integrate the energy storage in microgrid? Actually, there are also some challenges. Firstly, we need to select the proper type of energy storage according to the purpose in applications, such as peak power shaving and frequency regulation. In the second step, we also need to design the proper power converters to interface with energy storage. So in this scope, we need to select the proper types of power converters and design the parameters of power converters according to the characteristics of the energy storage. So the third point is about the system integration and the proper sizing of the energy storage. So in the system, it is also important to implement the energy management for several sources and loads. Then the last point would be the intelligent power flow control. So in this presentation, I will mainly focus on the system integration with the component sizing and energy management. So as mentioned before, in a microgrid, there will be several sources and loads. So it is not that easy to manage between the different components. But usually we can achieve this by formulating a mathematical problem and solving it by optimization algorithm. So how does optimization work here? Usually we need to find a specific problem and define some objectives. based on the objectives, we need to perform the mathematical modeling and formulate the optimization problem. And in the last step, we need to solve the problem, give the optimal solutions. So next, I will show the system architectures in data center and the residential community. So as well know that for a data center, it usually has high energy consumption with high downtime costs. To reduce the operational cost of the data center, it is necessary to have high energy efficiency and to have the high energy efficiency power conversion stage, and also with the possible green energy supply from the renewable energies. Due to the high downtime costs, there is also a backup energy source with redundant structure. So in the data centers, efficiency and availability are the main factors for data center. Here is a brief comparison of different topologies in data center. In conventional topology, it is based on the AC bus. So it requires many conversion stages to integrate renewable energies, diesel generator, utility grid, and the loads. It also shows high redundancy to improve the availability. On the other hand, in the conventional topology, the diesel generator and the lithium-ion battery are used as a backup power supply. So to reduce the power conversion stages, the DC bus-based topology is proposed. So as we can see here in the DC bus-based topology, it has a reduced power conversion stages with medium redundancy. But in the DC bus-based topology, we still use the diesel generator and the lithium-ion battery. So to achieve the high integration of renewable energies and also energy storage devices, the magnetic DC bus-based topology is proposed. So this is based on our ongoing project, which is called Superhat. With the multi-winding transformer, it only needs one conversion stage, so it can reduce the redundancy significantly. Also, with this topology, the hydrogen fuel cell and the supercapacitor can replace the diesel generator and the lithium-ion battery to achieve the green supply for the backup. So in a residential community, similarly, there are also several topologies. In the conventional architecture, a centralized low-frequency transformer is used to convert the medium voltage AC to low voltage AC. The renewable energies and energy storage devices are connected to the low voltage AC through some power converters and also low-frequency transformer. So in the conventional architecture, it shows low reliability and also more conversion stages. So nowadays, smart transformer-based architecture is proposed to improve the reliability, and also the conversion stages are reduced. So as we can see that the smart transformer provides the medium voltage DC and also low voltage DC. So in this case, the PV panels, wind turbines, and energy storage devices can be connected to the low voltage DC or medium voltage DC through some DC converters. So in a residential community, the load can be classified into non-critical loads and critical loads. For the non-critical loads, they are the loads, they are essential and can be interrupted without causing harm or inconvenience. So these non-critical loads usually include televisions, computers, and other electronics, and also offices. For For the critical loads, they are essential for daily life and cannot be disrupted without causing significant inconvenience and danger, such as hospital, household, and emergency lighting. So here, for the different types of loads, we propose to use different energy storage devices. As we can see here, this is a simplified topology for non-critical load and critical load. For the non-critical load, we propose to use distributed generator with battery energy storage to minimize the grid operation cost. And for the critical loads, we propose to use distributed generator with battery and hydrogen energy storage to achieve the self-sufficiency without the grid connection. So in the next part, I will show how the size and energy management are optimized, which will include the component modeling and the problem formulation. As an example, the distributed generator only includes the PV system in this presentation. So the PV generation is a function of the solar irradiance and the temperature. So these two figures show how, as the contour plots of the solar irradiance and the temperature. These two figures show how the solar irradiance and temperature change according to the different times in a day and also different days in a year. So according to the solar irradiance and temperature, we can get the PV efficiency. So as we can see that the PV efficiency increases at its beginning when the solar irradiance increased, and then when the solar irradiance increases further, the efficiency keeps almost constant. And also the efficiency is negative correlated with the ambient temperature. So when the temperature increases, the efficiency also decreases a little bit. So from the PV efficiency and also the solar energy, we can get the PV power production. The hydrogen energy storage system includes the fuel cell, electrolyzer, and hydrogen tank. So for the fuel cell, it converts the hydrogen energy into electricity. So the hydrogen consumption is a function of the supplied electric power. So we can see that this figure shows the blue line shows the system efficiency of the fuel cell, and the red line shows the hydrogen consumption rate changing with the electric power. So the hydrogen consumption rate is a function of the electric power. Similarly, for the electrolyzer, it converts the electricity to hydrogen. So the hydrogen production rate is also a function of the electric power. So according to the hydrogen net flow rate, we can get the hydrogen number of moles in the hydrogen tank. Basically, the hydrogen number of moles is the integration of the hydrogen net flow rate. For the battery, it can be modeled by an open circuit voltage and connected series with a resistor. So we can see that this is how the open circuit voltage changes with the state of charge. So if we consider the state of charge range with 30% and 80%, so the open circuit voltage is linearly changing with the state of charge. So according to the open circuit voltage, then we can get the terminal voltage of the battery and also the internal battery energy, also the battery terminal power. And also in the battery model, there is dynamics between the battery energy and the power. So the battery energy is the integration of the battery power. So in the optimization, we need to design the sizing of the components and also the optimal power allocations between the different components. So in this case, a generic code design optimization framework is formulated to minimize a cost function with respect to equality constraint G, inequality constraint H, and also system dynamics. So in this case, the cost function is formulated to minimize a summation of the capital cost and operation cost, depending on the different cases and also the appearance of the different components. The capital cost can include the purchase cost of fuel cell, battery, photovoltaic, electrolyzer, and hydrogen tank. For the operational cost, it usually includes the hydrogen cost and the electricity consumption cost. So for the different cases, we can select the state variables such as battery energy, hydrogen number of moles. For the constraints, usually the constraint will include the some power limit and energy limit for the different components, and also the number of moles limit for the hydrogen. So now I'm going to show some simulation results in data center and residential communities. For the data center application, we took the example from 100 kilowatt data center. So this figure shows the probability of power demand in 1 year operation. So as we can see here, the probability of power demand follows the normal distribution with the power range from 40 kilowatt to 75 kilowatt. And also the high probability occurs at 60 kilowatt. Regarding the design specifications, we consider the available rooftop PV panels, which is limited by the available roof area. And the battery is used as energy buffer. Here we also consider the time of use tariff to minimize the total cost. So this figure shows how the electricity unit price changes from for the different times in a day. So as we can see that the electricity is quite the morning time and also in the evening time, and for other time the price is relatively cheaper. So in this case, we can consider the different unit price to optimize the power allocations of the grid power and also the battery power. So after the optimization, we can get the optimal sizing of the photovoltaic PV panels and also the battery based on 1 year operation. So in this case study, we only consider the available rooftop area. So that is why the PV capacity is limited to be 31 kilowatt. And the battery is around 251 kilowatt hour. So this figure compares the different cases regarding the total cost in euros per day. So the first case is without PV panels and the batteries. So this cost is mainly from the grid, which is calculated based on the electricity consumption. For this case, it's with PV and battery. So we can see that the with the PV and the battery, the total cost is around 279 euros per day. So which shows 6% reduced compared to the case without PV and the battery. And also, actually, the operation cost is the major contribution to the total cost. The battery cost and the photovoltaic cost are relatively small compared to the total cost. So here I show the power allocations between different components in a typical day. So the black line shows the PV power generation. The blue line shows the load power. The green line shows the battery power, while the red line shows the grid power. So as we can see that the battery is mainly charged when the electricity is cheaper, and the battery is discharged when the electricity is more expensive. For the backup purpose, we consider 72 hours backup when the grid is not available. So this figure shows the efficiency map for the hydrogen fuel cell and diesel generator. So here we compare the operation cost regarding the hydrogen fuel cell and diesel generator. So as we can see here, the efficiency of the hydrogen fuel cell is much higher at the nominal power. So if we consider the diesel price, the current diesel price in Germany, which is around 1.72 euros per liter, based on the diesel price, we can calculate the diesel cost per day, which is around 1,000 euros per day. And by contrast, if we look at the green hydrogen price, which is around 9 euros per kilogram, so with this price, actually the hydrogen cost would be around 1,200 euros per day. But it is estimated that the green hydrogen price is going to drop in the following decades. For example, in 2050, the green hydrogen price would be around 3 euros per kilogram. So based on this price, so the hydrogen cost would drop to 400 euros per day. So based on this comparison, so actually it is quite promising to run the hydrogen fuel cell as the backup in the data center application. In another case study, we did the size and energy management for a 150 kilowatt residential community. So these two figures show the correlation between PV generation and the load power consumption for the office load and household load. So here the office load is considered to be non-critical load, and the household load is considered to be critical load. This is a normalized power regarding the PV generation and the load power consumption. Here I just show a typical day in different months. So we can see that so the red line is the PV generation, blue line is the load power consumption. So actually for the office load, the PV generation and load power consumption show better correlation. And also because the PV generation is calculated in Kiel in Germany. So the PV generation is more productive in the summer months, and then it's less productive in winter months. So for the household load, so the PV generation and the load power show a little bit worse correlation. So after the optimization here, I give the results for the optimal size based on 1 year operation. So for the office load, the PV capacity is around 244 kilowatt, and the battery is around 246 kilowatt hours. So for the household load, the PV capacity is like 1.3 megawatt, so which is much bigger than the peak power of the load consumption. So for the office load, due to the high correlation between the load consumption and the PV generation, so actually the PV capacity is around 1.8 times of the peak power demand. Well, for the household load, because the PV is the only source to achieve the self-sufficiency, so here the PV capacity is almost 8.7 times of the peak power demand. Then this figure shows the cost distribution for office load and household load. So the orange one shows the grid cost for office load. So here we can see that actually the operation cost from the grid is the highest one in the total cost. For the household load, so the main cost is from the PV cost and also the hydrogen tank cost. Because in the household load, we design the system to be the self-sufficient. So the PV is the only source to the system. So here the PV cost is quite high in among these different costs. So here is the power allocations in a year based on weekly average. So as we can see here, for the office load, the PV generation is almost used directly by the load in summertime. So because in summer the PV is more productive. And in winter time, due to the insufficient PV production, so in winter time the power is mainly provided by the grid. And also for the household load, so because the system is self-sufficient, so the PV is the only source. So here we can see that in summertime the PV provides power, the PV provides all the power to the load, and also the excess power will be converted to hydrogen through electrolyzer. As we can see, the purple bars shows the electrolyzer power. And in winter times, the PV production is not sufficient. So here we use the fuel cell to convert the hydrogen to convert the hydrogen to electricity to supply to the load. Then here comes the conclusion. So due to the unique characteristics of battery, supercapacitor, and hydrogen energy storage, the type of energy storage systems might be selected according to applications and purposes. As the battery and supercapacitor has high efficiency compared to the hydrogen energy storage, so the battery and supercapacitor might be suitable for short-term energy storage and buffers. The high energy density and hydrogen energy enables fuel cell and electrolyzer to be suitable for long-term and large-scale energy buffer and storage, like seasonal storage. For the data center applications, the hydrogen fuel cell is a promising solution to replace the diesel generator as a backup power supply. And And also the proper selection of energy storage, size and energy management can minimize operational cost and achieve self-sufficiency in residential community. So with this, thank you for your attention. If you have any questions, I'm pleased to answer.
Yeah, thank you very much, Qian. Just leave your presentation open for a second. I think we will, some applause. Great, thank you. We will maybe just talk about some slides that we have just seen. I think it was lots of information, and maybe we have some questions where we can just go back and have another look at one of the slides. So far, I don't see any questions in the chat. If you want to, you can also just ask them in German, and I will translate them really quick. It's no problem at all. So maybe I just start with some questions that I have. We have seen that the costs for hydrogen storage are really, really high in your case study for the households. How do you plan to store the hydrogen?
Yeah, because for the household load, the system is to be self-sufficient without the grid connection. So in this case, we have to store the electricity to hydrogen in summertime, and then in wintertime we have to use hydrogen to convert to electricity to provide the power. So that is why in this case the hydrogen tank is quite expensive. Yeah.
Since you just have to size it really big.
Yes.
I mean, compared to a battery that I have at my home, I just kind of charge it during the day and use the energy during the night, and then the size does not have to pick up so much energy, for example, from summer to winter. But hydrogen storage are utilizing compressed hydrogen, and then you of course have to take up so much energy that you reach even self-sufficiency during the winter days, right?
Yes. Yeah.
Okay,
so
I've seen that. Sorry.
Yeah. So if you have battery at home, then you can charge the battery in daytime and discharge the battery in night time. But in some case, I think in Germany now there are many people who install the battery at home and also the PV. But in this case, the system is still with a grid connection.
Okay, now we have a question from Tia Graske. In the simulation, has the heat demand and potential use of waste heat from electrolyzer and fuel cell been considered?
At this moment, no, I have not considered the wasted heat. So I just calculate the electric power consumption and electric power production.
Okay, so you also don't heat with the electricity, for example, in a heat pump or something.
No, I have not considered it yet, but I think the combined heat and the power is already a hot topic. So I think many people who are working on the combined heat and power. So in this case, because for the fuel cell, the chemical reaction is exothermic. So during the chemical reactions, it can also releases heat when it generates the electricity. So in that case, if the heat is reused to heat the water or something in the building, I think the efficiency of the fuel cell will also be improved.
And if you would include the heat, what do you think? Would you burn it in a turbine, or I mean the hydrogen, or would you use a fuel cell and then run a heat pump with it?
Yeah, basically we can use the fuel cell to generate electricity and heat at the same time.
Oh yeah, okay.
Yeah.
I wasn't sure if that's enough heat. I thought it wouldn't. Okay, then I maybe have another question regarding the energy management system that you mentioned. Who runs this system or who controls it? Because I think there are many decisions included, like when do we take the energy from the grid? When do we take the energy from the batteries? When do we produce hydrogen, or where do we even consume hydrogen? So I think it's all like artificial intelligence, right?
Yes. So actually, this power allocation can be operated by the grid operator, and also in smart home, I think it's also possible for people who live in the home to run this power allocation.
Okay, so in my household, I mean, I kind of work most of the time during the day. Like I work 8 hours, I have 8 hours of free time, and then I sleep 8 hours. That's my day, basically. I can't control it all the time. So I will not have my smartphone at my hand and say, okay, I have lots of PV power. Let's turn up the electrolyzer. I think there has to be a system behind to make those decisions for me, right?
Yes, there will be another controller from the system level, which will control each component, at which time it should be charged, or at which time it should be discharged, or something like that.
Oh, okay, yeah, that's great. That makes the system even more efficient and cheaper. Yeah, we have two more questions. Three more questions. First, Rolf Berndt has a question to page 29. The electrolyzer costs are extremely low. How is this possible? CapEx is currently perhaps 1,500 to 2,000 euro per kilowatt. I mean, he means the electrolysis.
Yeah, is it
Page 29, he mentioned.
Okay, page 29. Yes.
Yep.
Oh, yeah, this one. You mean the electricity cost for office load?
No, I think he mentioned that the electrolyzers are way more expensive that you have mentioned at the household.
Actually, okay. So for the household, so actually for the capital cost, like purchase cost of fuel cell and electrolyzer, they are just a one-time investment. So for example, if I buy the fuel cell or electrolyzer, maybe I can use it for 5 years or 10 years. Maybe in real applications, I guess the lifetime is not that long. But I mean, the capital cost is the one-time investment, but I suppose the system can operate for 10 years. Then I distribute this cost into every year. So actually, this cost is normalized as euros per day. So it means that the fuel cell cost and electrolyzer cost, indeed, they are expensive when you buy it at the beginning, but it means that you can use them for several years. But if you distribute this cost to every day, so actually this capital cost is very small.
Okay, yeah, that was really clear. Now I have let's stay on this page. I have two following questions from Tia Kraske. Assuming use of tank systems, how would the tank costs, hydrogen storage costs, change if based on area of application, geological formation, salt caverns, and so on, could be used to store hydrogen? So we already talked about that. At the moment, the hydrogen storage is really expensive when you use so many gas storages. And are there like other opportunities to make it cheaper?
Yeah, I think the hydrogen energy storage, yeah, it is quite expensive. So, but the reason why people develop the hydrogen energy storage is that we want to achieve the large scale and also large power storage. So, because for the large scale and large power storage, the battery cannot make it. For example, if you want to store a lot of electricity from summer to winter, so basically the battery will be sized for a very big capacity.
Yeah, and I mean, if you have a salt cavern at your household, you probably would use it. But I think in most of the cases, it's not really realistic.
Yeah.
But maybe you have it as a community and you can share it. Nobody knows.
Yeah, for a whole community, yeah. So the different homes can share this electricity and also the storage, all the cost. So
Yeah, of course. But in your case study, we look at households. I got it. Yeah. Last following question from Tia Kreske. How would tank costs change or minimize if grid would also be used? So the not self-sufficient designs. At the moment, the household is quite expensive, as you mentioned, because we want to be 100% self-sufficient. How would the cost minimize or, yeah, like decrease a little bit if we would be connected to the grid?
Yeah, so it depends on how much electricity you can buy from the grid. So and also depending on the problem formulation. So in that case, we will have some amount of operation cost from the grid. So I'm not sure the total cost will be reduced or not, but so there are different configurations. So for the configuration from my side, now it is self-sufficient. But if it is not self-sufficient, then we can define that how much percent of the energy can be bought from the grid. Then we for the remaining energy demand, then we can provide from PV and also the battery and also the hydrogen storage.
Yeah, I mean, that's also something that the energy management system would decide for me, right? Like when the energy system sees that at the moment the electricity from the grid is cheaper than running a fuel cell and producing electricity from a hydrogen storage, I think the energy system would make this decision, right?
Yes.
Okay, now I have one question from Klaus Taube from Herion. Could you please explain the monthly correlation between office load and PV power production? Why are there monthly peaks of power consumption and production? Maybe you can also just go to the slide where we have seen the peaks.
Yeah,
exactly.
it's this one. Yes. Yeah, so actually this figure shows the PV generation and the load power consumption for a day. So for example, for 1 month, I selected 1 day to represent the PV generation and the load consumption. So in practice, because the people needed to go to office from 8 o'clock in the morning and 6 o'clock, maybe 5 o'clock in the evening. So but also the PV generation provides most power in the daytime. So that is why the PV generation and the load power consumption show a better correlation. This is also the method to calculate this correlation. It's called, I don't remember the name. So just to use the PV power production and the load power consumption to calculate how these two variables are linked. I'm not sure the question. So
I think you already answered it, that
okay.
it was just a day within the, yeah, okay, yeah, exactly. Klaus Tauber already said, yeah, that was the case, so thank you. Yeah, let's go on with the next question that we have right here from Tobias Kors. First of all, thank you for your presentation. Could you elaborate more on the modeling approach, especially on input, considered stochastics, and model type, mathematical optimization or simulation?
So maybe we can go back to the modeling part.
You can also open the chat when the questions are too long to just follow me, okay?
Okay, yeah. Yeah, so for this modeling part, it's just the basic relation. So for example, for the PV generation, it's just a function of the solar irradiance and the ambient temperature. So in this case, we need to find how exactly the equation are regarding the PV generation and the solar irradiance and temperature. So here, for the PV generation, the power is calculated from the PV efficiency, and this A represents the active area for the PV panels, and this J is the solar irradiance. So once we know how big the PV panels, how big the PV panel is, and also the solar irradiance, so we can get the solar energy from this active area A and the solar irradiance J. Then there's another equation regarding how to calculate the PV efficiency from the solar irradiance and the temperature. Yeah, so from the solar irradiance and temperature, then we can get the PV generation. So basically, this is a very simple equation. So it's quite easy to find from the published literature.
So it was a mathematical approach, not like a software or something.
They are just mathematical equations.
Okay.
Yeah, because for the irradiance and temperature, we can download from some public source for different years and also different days. Then we just apply some basic equations, and also for this hydrogen energy storage. So as we all know that the fuel cell converts the hydrogen and generates the electricity. So this hydrogen consumption rate is also like a mathematical function of the electric power. Similarly, for the electrolyzer, it's the same. So we just, because in the energy management layer, it's like the high level, the system level study. So here we only consider how much hydrogen is consumed from the how much hydrogen is consumed from the fuel cell and how much power is generated according to the hydrogen. Then for the electrolyzer, it's in a reverse way. So we need to know how much hydrogen is produced from the electric power. So actually, we can use the curve fitting method to get this mathematical equation between the hydrogen consumption rate or hydrogen production rate and the electric power. So for the battery, because here I just use a very simple model. So it's the open circuit voltage connected in series with a resistor. Then this is based on the equivalent circuit model. So from this equivalent circuit, we can get the voltage, battery energy, and power.
Okay, we are running out of time, but I would like to pick up the last two questions. The first one, I'm not sure if this is actually part of your research. If it's not, just let us know, because you already mentioned that heating is not included within your case study. But the question from Rolf Berndt is, how does household solution PV and fuel cell compare to heat pump?
Oh, yeah, I have not compared this, but but it would be very interesting to do such comparative analysis heat pump.
Yeah, okay. Yeah, I already thought that it's not part of your model, but it's a really interesting question, obviously. Yeah. Then I would like to pick up the last question from today from Klaus Taube. Once again, concerning the hydrogen storage system. Do your figures just consider investment costs for the storage system or also operational costs? So, for example, connected with operation and power consumption of a compressor.
Okay. Here I just consider the investment cost for the hydrogen tank. Then I consider the hydrogen is stored in nominal conditions. So here the hydrogen tank is the unit for the hydrogen tank is nominal cubic meters. So then in this case, I don't need the compressor. And yeah, then I also don't need to consider the investment cost for the compressor.
Oh, okay. But wouldn't it be cheaper if you compress it and then need less storages?
Yeah, that could also be one interesting question. But the thing is that, yeah, if you compress the hydrogen, it means that you will have smaller volume. But the hydrogen tank would also be more expensive because the cost of the unit price for hydrogen tank is also depends on the pressure. So the higher pressure you have, then you also have the more expensive of the hydrogen tank.
Yeah, okay. Yeah, I already thought that my thinking was a bit too easy. Okay, yeah, we have just a few minutes left, so I would like to thank you for your great presentation and also for this really interesting Q&A session. I hope that afterwards you will have some more interesting contacts who like to continue talking with you about your research or even present their research to you. And yeah, to all the participants, as you might know, we will send you this presentation and the also the video afterwards. The next lunch break we don't know yet, but maybe there will be one more in July, or in July and August we will start with our summer break. We are not sure yet, but maybe there will be one in July, or maybe we will just see each other in September. But today it was a really great presentation we had with Qian. And if you have further question, feel free to just send her an email. Then you can get in contact with her directly. We will just put her within the email that we will send to you as a follow-up email. I see some applause down here. That's a great sign. And yeah, thank you, Qian, and have a good week.
Thank you. Have a good week. Bye.